Alright, welcome to the notes on the periodic table. We'll start off here with a little bit of recognition for Mr. Dmitry Mendeleev, and he is the one that created the first meaningful periodic table in 1869. Prior to him, people were trying to clump all the elements together and try to put them in some sort of fashion, but what he did that was remarkable was that he left blank spaces. He took elements, and if they happened to react the same way, then he would group them together. He didn't force all the elements to be crammed together like many of the other people did. So by leaving these blank spaces, it just opened up this wonderful world of predictability. And so he would predict what these elements that weren't there were really like. And so one of the first ones that came into existence was gallium. And when gallium was discovered, it actually fit right into one of the empty spaces that Mendeleev had left, and the properties that he predicted were almost spot on. And he was exalted and praised for creating this wonderful, wonderful grouping of the elements. And now, when you look at the periodic table, all the spots are filled in that he had left blank. So again, it was quite remarkable for that time. Now, there's a reason it's called the periodic table and not just the list of the elements or the table of the elements. It comes from the definition of the word periodic. So if we go here and check out the definition of periodic, you can see that periodic means occurring at intervals. And that's like in the old days, we used to call magazine periodicals because they would come at a regularly scheduled interval. Now, along with that, as you can see relating to the periodic table, would be the pattern of chemical properties. So, for periodic, occurring at intervals, in parentheses, the pattern of chemical properties. And the reason it's called the periodic table is because we see this repeating pattern throughout the periods. The periodic table is organized by 7 horizontal rows, which we do call the periods, and then there are 18 vertical columns, which we call groups or families. And like I said, Mendeleev was grouping the elements together, and so he put them into these groups. And then they're called families because he did this because the elements that he did group together related in the same way, much like you are related to your family. And that has everything to do with electron configuration. The elements end up in their families due to this, where the electrons are. Like DNA to us, linking us to our families, it's these electrons, and specifically the valence electrons. And as we mentioned in class before, and we'll talk about more later, those are the electrons in the outermost energy level of the atom. They're the ones responsible for most of the chemistry that we deal with. And so we have these groupings of the periodic table, and there are some special families, as we'll see here. Ooh. Group 1 we call the alkali metals, and you'll notice that I have an X where hydrogen would be. Hydrogen belongs there, but it's not technically a metal. Next door are the alkaline earth metals, and those are in the next door neighbor, right there, the alkaline earth metals in group 2. And then across the way we have halogens and the biggies, the noble gases, that we'll be looking at quite extensively throughout the year. So let's start with those noble gases. They are also known as the inert or non-reactive gases. They are the most stable elements, and that's probably the key there, the most stable elements. And they really don't react with any other elements. We've been able to get xenon to react a little bit in the laboratory, but really not much. And you can see the beautiful colors that they produce when electricity is passed through them. As I talked about in class that one day, a true neon light is just neon, but you can see the noble gases used for many of the other colors seen there. Radon is kind of bad for us. It can seep in your house through the basement, and many parts of the country you have to have radon detectors. Not so prevalent here due to our sandy soil being by Lake Erie, but it is something to look out for, perhaps in other areas. The noble gases are neighbors to the halogens, which are the most reactive nonmetals: fluorine, chlorine, bromine, and iodine. Astatine is there in the group, but it's in such insignificant amounts on this planet that it's really chemically irrelevant. Fluorine, a very reactive element, is what we've been able to get xenon to react with in the laboratory. So you can tell it's an extremely reactive element in order to get a noble gas to react. On the flip side, we have the most reactive metals, the alkali metals. And those are in group 1. Even if they get introduced to water, you can have explosive results. All of these metals, when they go into water, will produce hydrogen gas, which is flammable, and you can get quite an explosion. Lithium, when you put it into water, it just fizzes a little bit. A little bit of hydrogen is produced. Sodium, you can see a little flame ignite. Potassium can actually explode. And then rubidium, cesium, and francium, we get ginormous reactions. And that's what we call a periodic trend. So Mendeleev grouped them together because of how they all reacted with the water. And then the trend is, as you go down that group, the reaction gets a little more and more and more explosive. These alkali metals love to hang out with and react with the halogens. Sodium is an alkali metal. Chlorine is a halogen. Sodium chloride is one of the most prominent substances on this planet, and we'll get into more of that in the next coming units. The last little group to look at, the alkaline earth metals. We saw a lot of these in the flame test lab. A lot of them were on your fireworks web quest, as they do add a lot to our fireworks. But what we have them here for, they're a model group for those periodic trends that I just mentioned. And we will be talking more about those in the future here.